Okay, we're going to start our study of forces by considering Newton's three laws of motion. Now, Newton famously published a work called the Philosophiae Naturalis Principia Mathematica, also known as the Principia. That's Latin, of course, and it translates into English as the mathematical principles of natural philosophy. And the key word here is principia, which is the principles. So the mathematical principles of natural philosophy. Now, the words natural philosophy here, that's what they used to call science. And so if Newton were publishing his book today, he might call it the Mathematical Principles of Science. It was published way back in 1687, and in it, Isaac Newton formulated his famous law of universal gravitation and his three laws of motion. And in the next series of video lectures, we're going to be looking at these different laws and how they can be applied. Now, the first law of Newton, Newton's first law of motion, that's the law of motion. Newton's first law of motion says that an object at rest will remain at rest unless it's acted upon by a net external force. And secondly, it says that an object in a state of uniform, that means constant velocity, motion, will maintain that state of motion unless it's acted on by some net external force. And of course, I've found this meme on the internet that says, inertia. Your truck has brakes, the massive hunk of stone doesn't. So what happened here was the truck hit its brakes. It was carrying this giant stone in the back. So the truck slowed down, but the giant stone, it kept moving forward. And so the truck basically slowed down out from underneath the stone. But from the perspective of the guy in the cab, it seemed like the stone lurched forward and smashed into him from behind. This idea comes from Newton's first law. So this object, the truck and the stone, they were moving together. The truck slows down, but the stone keeps its motion because the friction between the stone and the floor of the truck bed was not enough to slow the stone down. And so Newton's first law says that whatever you have, whatever motion you have, you're going to want to keep that motion. And if you want to change that motion, you have to apply a force. Okay, here is an application of that Newton's first law, which the first part of it says an object at rest will remain at rest unless acted on by some net external force. So I've got this ball in a wagon here, and the wagon, someone grabs the handle of the wagon and jerks it forward. And from someone standing outside the wagon, it looks like the ball will roll to the back. But what's actually happening is the ball and the wagon are initially at rest, and they want to stay at rest. And the only way that you can change their motion is to apply a force. And so a force is applied to the wagon, but the ball basically stays where it is. And so you can see in these pictures, the wagon is moving forward, but the ball is keeping in the same position as where it was. And so it seems like the ball is moving or rolling to the back, but really, the Newton's first law is telling us that that object is going to stay where it is. Now, if you pull the wagon very slowly, what will happen is that the friction between the floor of the wagon and the ball will be able to drag the ball with it. And so you can move them together if the friction is strong enough. But if you give it a good jerk, the friction won't be able to provide enough force to accelerate the ball with the wagon, and so the ball will basically stay where it is. This is the same principle if you've ever seen the magic trick where the magician has a place setting on a table under a tablecloth. There's candles and silverware and plates, and he jerks the tablecloth out from under it, and everything just stays in place. They don't come crashing into the floor. It's the same principle. The jerking of the tablecloth is creating such an acceleration of the tablecloth that the friction between the tablecloth and the candle and the plates and whatnot, it cannot drag the plates. It cannot provide enough force to accelerate those things with the tablecloth, and so they get left behind. But if you drag the tablecloth slowly, the friction can provide enough force to accelerate those things with the tablecloth, and they'll all come crashing to the ground. That's an application of Newton's first law of motion. Okay, so here we have Newton's first law with another application. Now the second part of Newton's first law says that an object in a state of uniform, that means constant velocity, motion, will maintain that state of motion unless it's acted upon by some net external force. So here we have a car moving, there's a ball or something in the car, and they're moving together, but then the car brakes. And so the car is slowing down, that means its acceleration is going to be in the opposite direction, but what's going to happen is the ball is going to keep moving forward. And so the car basically comes to rest, but that ball is going to move forward because it wants to maintain the velocity that it already had. And in order to slow the ball down, you have to apply a force to it. Now again, it's the same principle. There's some friction between the ball and the floor of the car, or the seat of the car, wherever the ball's sitting. And so if the car brakes slowly, if there's a slow acceleration, there won't need to be a big force, and so the ball can slow down with the car. But if there's a quick braking, if someone slams on their brakes, that ball is going to seem to fly forward in the front of the car. And you guys have all seen this. You've had something on the seat of your car, you hit your brakes, and the thing goes into the floor of the car. Or you slam on your brakes and you feel yourself almost like you're being thrown into the steering wheel. This is because you and the car are moving together, but then the car brakes, it's literally slowing down out from underneath you. And you're maintaining the motion you have. That is the principle behind Newton's first law. Now, this also applies to centripetal or turning accelerations. And so here I have a car that is moving with the ball, and they're moving together, and then the car turns. Well, the ball is going to keep moving in a straight line, but because the car is turning out from underneath the ball seems to go to the side of the car. So it feels like there's this horizontal force pushing it against, perpendicular to the velocity. But what's really going on is the ball is just maintaining its motion, and the car is turning out from underneath it. Now, that usual way of writing down Newton's first law is pretty long, and there's this way that you can summarize it that's a little bit more compact. And the way that I usually like to express Newton's first law is like this. To accelerate an object, that means to slow it down, to speed it up, or to make it turn, one must apply a net external force. Now, what do we mean by net external force? So, external force means a force that's coming from outside the body, and net force means that there is an excess of force. In other words, if I have a block here, and I apply 10 pounds like that, and I apply 5 pounds like that, there's going to be a 5-pound net force to the right. And by the way, that part about it being to the right is important, because force is a vector, and that means that it has a direction as well as a magnitude. Now, if I take that same block and I subject it to 10 pounds from the left and 10 pounds of force from the right, that block may smush a little bit, but it is not going to accelerate because there is no net force. This force and that force will cancel each other out. They're balanced. But here, I've got a 10-pound force that's overwhelming the 5-pound force, and you end up with a net force of 5 pounds. And when there's a net force, that means you're going to have an acceleration. Not just movement, but acceleration. Now, experiments show that acceleration is proportional to force. In other words, if I've got a mass, and here's a mass, and I apply a force to it, I'm going to get an acceleration. But if I double the force, so now I've got twice as much force pulling, I end up with double the acceleration. If I increase the force 3 times, I get 3 times acceleration. So however much you increase the force, that mass is going to accelerate by that much more. Now, experiments also show that the acceleration is inversely proportional to the mass. And so, in other words, if I have a mass and I have a force, I'm going to get a certain acceleration. If I keep the force the same, but I double the mass, I end up with half the acceleration. So twice the mass gives me half the acceleration. And you can see the formula here, A is equal to F over M. This is the acceleration. That's the mass. And that F is the net force. And this relationship, A is equal to F over M, that is known as Newton's second law of motion. So here we have it written down, and we can see that Newton's second law tells us that the acceleration is equal to the net force divided by the mass. And by the way, very often you'll see the net force written as the summation of the forces, and you guys may have seen that symbol in your math classes. That's the Greek capital letter sigma, but it just means add up all the forces, and then you divide by the mass, and that gives you the acceleration. Now, notice also that there is an arrow on top of the F and an arrow on top of the A, because both of those are vectors. And so when we say the sum of the forces, that means we have to sum them up like vectors. And we know what that means now. That means break them down into components, add the components, and then put them back together with trig in your Pythagorean theorem. And by the way, so I've used pounds a lot when I've talked about forces, but when we're dealing with the SI system, or the metric system as it's sometimes called, the typical unit of force is called the Newton, and mass is generally measured in kilograms, and of course we know acceleration is in meters per second squared. But a Newton is about a quarter of a pound, not quite a quarter of a pound, and a kilogram has a weight equivalent to about a little bit more than 2 pounds. 2.2 pounds is the weight of 1 kilogram. Okay, so the SI unit of force is the Newton, and SI, that stands for the International System, and it actually comes from France, so it's the Système International, but we like to think of it just as the metric system here in the States. So this is the unit of force in the metric system. It's called the Newton, and 1 Newton is the amount of force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. And so we see F equals ma, so 1 Newton is equal to 1 kilogram times 1 meter per second squared. That's F equals ma. And so that's what we mean. So if I take a 1 kilogram mass and I accelerate it by 1 meter per second squared, it's going to take 1 Newton of force to do that. And interestingly, a medium-sized apple weighs about a Newton. So you guys might have heard the story of the apple that fell on Isaac Newton's head. But if you're trying to think about how much a Newton weighs, you can think about how much a good-sized apple feels in your hand, or just kind of judge it like not quite a quarter of a pound. The imperial unit of force is the pound, and we've used that quite a bit already. Everyone in the United States is very familiar with the unit of pound for force, but in the states who are less familiar with the metric system units, we just kind of roll that way here in the States, but the unit of force is the Newton. But when you're dealing with the metric system, more commonly people use kilograms. They think of things in terms of mass instead of force. Now Newton's third law, we've got the first law, we've got the second law, here's the third law. For every force, there is an equal but opposite reaction force. So if this guy is pulling on a crate with a rope, there's going to be forces transmitted through this rope in both directions. There's going to be the force of the man pulling on the crate, and then the crate is going to pull back on the dude, and he's going to feel himself being forward. So you could imagine if this was a very slick surface here, if they were on ice or something, and the crate was very, very heavy, and the guy starts pulling on the crate, he might actually feel himself pulled towards the crate rather than the crate pulled towards him. That's because there are these equal and opposite forces. But if the guy has good traction with the ground, he might be able to drag the crate forward. Now, someone who read Newton's third law, that for every force there's an equal and opposite reaction force, they might say, or they might ask, why don't those forces cancel each other out? That would seem to prevent any possibility of acceleration. And the resolution of this paradox comes from realizing that these Newton third law forces, they always act on different bodies. So what do we mean by that? So here I've got my guy pulling the crate again, and so we've got the force of the man acting on the crate, and the force of the crate acting on the man. Well, this force up above, it's acting on the crate. And so the force below, it's acting on the man. And so is the crate going to move or not? So why don't these two forces cancel? Well, this force is acting on this object, this force is acting on that object. They're not acting on the same object. So if I want to know, is this crate going to accelerate? Is it going to start moving? I might look at, say, for example, the friction with the floor. Oops. And so there might be some friction there. And I can say, okay, now I can look at the forces on the crate. And if this force is bigger than that force, then the crate's going to move to the right. It's that simple. This force here, however, the force of the crate acting on the guy, it has no effect on the crate at all because it's not acting on the crate. So yes, these are equal and opposite forces here, but they act on different objects, so they don't cancel. Now we're going to see an exception to that later on, but as a general rule, that's the principle. Now here's a conceptual example for you to think about, and this is again an example involving Newton's third law. So the example says a 10,000-pound semi-truck moving 100 miles per hour collides head-on with a 2,000-pound Volkswagen Bug. So the semi-truck weighs 5 times as much as the Volkswagen Bug. They're both moving 100 miles per hour in opposite directions, and they crash together. Which of these two statements is true? Statement A says the Volkswagen Bug receives a larger force in the collision. Or statement B, the semi-truck receives a larger force in the collision. So which force is going to be larger, the force acting on the bug or the force acting on the semi-truck? And the answer is, it's a trick question. So, what does Newton's third law tell us about these forces? So when they collide together, when there's a collision, we've got this kapow here, pow, they collide, what's going to happen? They're pushing against one another. And according to Newton's third law, when one pushes against the other pushes back with an equal but opposite force. And so neither force is bigger, they're the same force. And yet, most people would have an intuitive sense or an intuition that the Volkswagen should be the one that gets the bigger force. And the reason for that is the acceleration. Remember, the acceleration is the force divided by the mass. And so the acceleration of the Volkswagen with the same force is going to be much bigger because you're dividing by a much smaller mass. And so these two guys collide, and the Volkswagen seems to get knocked to heck and back. But the forces are the same. And so visually it looks like the Volkswagen Bug is getting a bigger force because it gets a bigger acceleration, but that's only because it has a smaller mass. The forces are the same. And so that concludes our discussion of Newton's three laws of motion.